Welcome to our webinar, CATT, New Multi-Sample Measuring Technology for Adhesive Bonds, Tensile Strengths, Coatings and Composites. We will introduce you to a new analyzer called LUMiFrac and a new technology called CATT technology. Both offer you great possibilities for testing of adhesion, bonding, tensile and shear strength, and also will save you over 80% of time usually needed for testing and requires no sample clamping at all. We will give you a short introduction in CATT technology and the sample preparation. We'll present a selection of measurement results and show you step by step how easily you can operate this analyzer by yourself. Our new multi-sample measurement principle CATT technology determines adhesive, bonding and composite strength by detecting automatically the critical failure load of up to 8 samples tested simultaneously. The centrifugal force is calculated by the given equation, where m is the test stamp mass, r its distance to the rotational axis, and omega the angular velocity. Dividing the breaking force by bonding area results in strength sigma. CATT technology meets common standards as. Here we show you how it works. Centrifugal force is applied to up to 8 test specimens in a special rotor, which runs at up to 13,000 revolutions per minute. A load increase is programmed by variation of rotor RPM or directly. By accelerating the rotor, the test load increases until the test stamps separate from the samples. At the precise moment when the detachment of the test stamp occurs, a position-coded signal is sent out of the turning rotor, transmitting the current rotor speed as well as the rupture time. Now the breaking force is calculated by LUM's own measurement software, SAPview, taking into account the test stamp mass and its distance from the rotational axis. With the LUMiFrac, you can now quickly and efficiently test the adhesive strength and plastoelastic properties in a broad range of applications for bondings and coated surfaces. As in other methods, the preparation of test specimens is necessary prior to testing. We will now show you in detail how to prepare a test specimen for testing in LUMiFrac. A test specimen basically consists of the following components. First, a sample, either a pure or a coated substrate. Second, a test stamp consisting of a mass body and adherent. Third, a guiding sleeve. And fourth, an adhesive. The adhesive, if not being the subject of interest itself, is necessary to connect the test stamp to the sample. Here you can see how that works in real life. First, the adhesive is applied onto the test stamp's adherent surface. Now the test stamp is inserted into the guiding sleeve, which has been placed on the sample surface. The test stamp is moved downward and attached to the substrate. During the joining process, the stamp is guided by the sleeve. In contrast to tensile testing, the preparation of shear specimen is different. The test specimen consists of 2 adherents, a set screw, a mass body, and, again, a guiding sleeve. As shown, the parts are joined separately. The small shear adherent is covered with adhesive, turned around 180 degrees and bonded to the broader counterpart. Afterwards, adhesive curing takes place. Time and temperature are to be considered. Here you see shear specimen preparation for real. In this example, the yellow release paper is used to ensure bonding of the shear area only. Prior to testing, the mass body is assembled by a set screw and the guiding sleeve is slid on. You can see how simple preparation and assembly are in our case. Now that we have prepared the test specimens, we can move on to assembly them and proceed putting them into the detection modules which are housed in the LUMiFrac. We now take them out and begin to join every specimen into one module. The modules are then loaded into the rotor one by one. In this instance, you see we fully load the rotor, but of course you can test any equal quantity like 2, 4 or 6. You can test tensile and shear specimen together in one run. When the chosen number of modules is equipped, we close rotor and centrifuge lid. We then start the physical measurement and simultaneously open the SEP view, short for separation view, software on our computer. Create a new SOP by clicking on the corresponding buttons. The SOP wizard opens to conduct the necessary settings. Name the SOP, then enter the names of your samples and select the test stamps to be used. Predefined test stamps can be selected by clicking on a drop-down menu. Measurement parameters are operational defaults of the analytical centrifuge. They depend on materials used, like different types of adherents and adhesives. The 4 measurement types allow for 2 kinds of standard short-term testing as well as 2 special long-term measurement options. Clicking on the Execute button advances you to the fracture recorder. Here you can change measurement name, sample names, masses, distances, or areas if desired. You can also add additional comments to the measurement and individually for each test specimen. The device is shown in the lower left section of the fracture recorder window with information on rotor balance at the top right side. See here how we can adjust all the different settings for every sample at once. By pressing the Equilibrate button, you can temperature equilibrate the active cooled product line. By pressing the Measure button, you can start the measurement. During the measurement, speed and temperature are displayed in real time in the device status graph in the upper part of the recorder window. The current applied loads for each sample are shown in the lower chart as vertical blue bars. When a sample detaches, a gray bar next to the blue bar shows the rupture or breaking force for the corresponding sample. See now how the breaking force is displayed for all of our samples. Now we can stop the measurement. We see the final results for every specimen, which are shown numerically and in diagrams. We now have several options to continue. Download the measurement as an Excel file or continue in our browser-based view, where we click on the View in Browser option in the fracture recorder, or by clicking on the measurement name in the project content page of the Explorer. Here you see a detailed display of all your measurement details. Samples can be individually specified by uploading fracture images and by adding additional information, for example, used adhesive, coating, substrate material, or comments regarding the fracture behavior. The device status, the speed and temperature settings, the duration, all are saved here for a convenient evaluation. You can also tag with keywords that can be easily searched and found later in your database. Here we click in the detailed view for our sample 1. Again, we have options for every single sample, like Excel export and a rewatch of the recorded analyses. Another interesting feature is the image upload, where you can make a picture of your ruptured specimen and assign it to the specific sample. By clicking the Analyze button, a new analysis window for the measurement is opened. The results for every specimen are shown numerically and in diagrams. The Statistics box allows choosing between breaking force, strength, measurement time, or RPM as values for the graph shown in the Comparison box. The individual information for each sample is shown in the Specimens box. Samples, also from different measurements of the same project, can be added or removed from the analysis by clicking the corresponding buttons. The diagram in the comparison box can be grouped by up to 2 selected characteristics, for example, measurement, adhesive, substrate, etc. A manual option gives you maximum freedom to sort and arrange in your preferred way. The measurement either stops automatically or by a simple click on the Stop button. As you can see, all the substrates have fallen off. Returning to our analysis, we now show you the corresponding Excel files after download. The measurement results are shown left of the export file along with mean and standard deviation. The test stamp data are listed on the right. The numerical data from the speed and temperature graph are listed on the Device Status spreadsheet. Now we move on to a part that we are most interested in, the application examples. There are measurements of different adhesives and composites that our customers did with us in the last 3 years. Example 1. Polymers like PA polyamide or PP polypropylene are characterized by low surface energy. Therefore, joining by adhesive bonding often results in insufficient bond strength. Plasma treatment significantly increases the adhesion properties of the mentioned polymers. The process of plasma treatment in this example was applied as follows. The samples are placed on a rotating tray. After plasma ignition, the tray is moved below the plasma burner where the 8 samples were treated. After plasma treatment, the PA and PP substrates were bonded to stainless steel adapters using a 2-component epoxy adhesive. The diagram shows the influence of different treatment conditions. The tray was rotated with 4 different speeds, which can be seen on the x-axis. PP, which has a lower surface energy, 32 millinewton per meter compared to PA, 43 millinewton, always shows lower strength. Even after plasma treatment, the ranking of the polymers used is the same as before treatment. The positive effect of plasma treatment on adhesive properties can be seen in an increase of strength. The optimum rotation speed in this case is 15 rpm. Both polymers exhibit highest strength at this RPM. Users who would like to find out more about the further processing possibilities of their products manufactured by adhesive bonding may have a look at the next example. The curing behavior of a 2-component polyurethane adhesive is discussed with regard to strength. At the beginning, 40 test specimens were prepared simultaneously. Both adherents consist of stainless steel. With an interval of 30 minutes, 4 specimens were tested. The diagram shows the strength development over time of the adhesive. The handling strength is the minimum strength of a bonded joint which is needed to continue further processing without influencing joint properties. The time required to reach handling strength, often equated with the attainment of a certain strength value, is of great importance to reduce overall production time. Examples are, for instance, car windscreens, rotors for wind power plants, or electronic components on circuit boards. As specified by the manufacturer, a handling strength of at least 2 megapascal is required. This threshold was exceeded after 3 hours of curing. During the first 2 hours of curing, bonding strength is increasing rather slowly. The remaining 3 hours of curing show a steep increase of bonding strength towards final strength. Progressive strength development was determined. For applications which require faster curing, other adhesives could be evaluated or curing conditions optimized. Our next example shows a measurement that was carried out to compare strength results with the provided data of the adhesive manufacturer, which were determined by using common ISO and DIN standards. Measurements such as this are important for incoming goods inspections, especially for sensitive applications like in aviation, car or aerospace industry. The used adhesive was a polyurethane adhesive bonded to stainless steel. Tensile strength was determined using 2 different test clamp types, a light and a heavy one, to show the independency of strength from the weight of the mass body. In the right section, shear strength is illustrated, again using light and heavy test stamps. Equal strength values have been determined for each stress orientation. Generally speaking, the detachments occur at lower RPM for the large and heavy test stamps than for the medium and lighter test stamps, but the resulting strength is similar. This allows to vary the applied testing force in a range by changing the test stamp's mass body without influencing the results. The measured values in this case were in compliance with the technical data given by the adhesive manufacturer, confirmation that the used adhesive is of high quality and the product still fully operational. All 3 application examples prove that LUMiFrac using CAT technology is an excellent research and quality control tool for all kinds of industries dealing with adhesives and composites. Thank you for your attention. We are looking forward to receiving your questions by email to info@lum-gmbh.de.